We know that graph convolution to update node embeddings for each node in your original graph structure involves message parsing, and message passing involves transformation and aggregation of messages. Let's look at the math involved. We look at it at a very high level, and even though what you see here on the screen is quite complex, I'll break this down step by step. Every node in the graph that you feed into the graph neural network contains node features. Initially, at the zero layer of the graph neural network, the embeddings of each node are just the node's features, and these features can be thought of and represented as HV of 0, where 0 represents the zero layer of the graph. Now, let's say your GNN has a total of capital L layers. The node embeddings after L layers of neighborhood aggregation are represented as HV superscript L or Z of V. These are the final embeddings for every node in your graph. Now, how did we get from the initial node features to the final embeddings using this formula? Now, I know this formula looks kind of daunting, but don't worry, we'll break this down. So these are the transformations and aggregations that we'll perform to go from the initial node features to the final embeddings. The math that you see here is basically the observation of node embeddings in each layer of the graph neural network. The final objective is to find the embedding for a node V, that is, the subscript at the next layer of the graph layer L plus 1. To find the node embeddings at the next layer, you of course need to work with the node embeddings at the current layer. H of V at L is the embedding of the node V at the current layer L. This current layer's node embedding is transformed by parsing it through a neural network layer, and I've represented that as B of L. This is just a learnable matrix. Now, in order to update the current node's embeddings, we need to take into account the embeddings of the neighboring nodes as well. That's represented here by HU of L. This is the embedding at the previous layer for every node U that is a neighbor of the node V. Now, graph convolution usually involves neighborhood normalization. The embeddings of the neighboring nodes are normalized using the number of neighbors of node V. The normalized node embeddings of neighboring nodes are then aggregated over all of the neighbors of the current node V. And this aggregation is a permutation invariant aggregation such as sum, average, or max. The aggregated node embeddings of the neighbors are transformed using another neural network of learnable parameters, and that's represented by WL. This is the current neural network layer. And finally, this entire result is parsed through an activation function, which introduces some non-linearity in the neural network, and this gives us the embeddings for the next layer. Apply this transformation to every layer of the graph neural network and run this for several iterations, and this will give us the final embedding for every node in our original graph structure at the last layer. The layers of the neural network are represented by these learnable parameters W of L and B of L. These are the trainable parameters in the neural network, and this is it. This is the aggregation and transformation math that a graph neural network performs under the hood. These operations seem complex, but they can be performed very efficiently using matrix transformations. We'll shortly move on to discuss graph attention networks. Now, before we get there, I'm going to simplify this representation that you see here on screen. Here is a simplified representation of the math to get the node embeddings at the output of a certain layer. This simplified representation is equal to the previous representation that we've seen. What I've done here is I've added a self loop to every node in the adjacency matrix. Adding the self loop means that every node is a neighbor of itself, so you do not have to consider the node's own embeddings separately. The node's own embeddings will be considered as a part of the neighborhood information for the node. The addition of the self loop is what allows us to simplify the math of the aggregation and transformation operation in graph convolution. Now that we've included a self loop in the graph, we have a single weight matrix with the learnable parameters for the model. These are the learnable parameters for the neighboring nodes as well as the current node. So we don't have two different neural network layers. We just have a single neural network to learn parameters for the node itself and all of its neighbors.